In this example problem, we're going to look closer at the binomial and normal distributions using an example of HIV prevalence in South Africa. So read the example provided on the web page, and the important things to note in this example specifically are that we have a random variable x, which is the number of HIV positive individuals in our sample. We've taken a sample of size 500, and the prevalence of HIV in this population is 17.8%. So N equals 500, P is equal to 17.8%. How many individuals do we expect to be HIV positive, and what is the standard deviation of the number of HIV positive individuals? To do those calculations, we would say the expected value of X is equal to N times P, which is equal to 500 times 0.178. And doing that calculation, we find that we would expect on average 89 individuals to be HIV positive. Next, we want to know the standard deviation of X. It's equal to the square root of N times P times 1 minus P, which in this case is the square root of 500 times 0.178 times 1 minus 0.178. Plugging that into a calculator, we find that the standard deviation is about 8.55. Next, we want to do some probability calculations. First, what is the probability of observing more than 100 HIV positive individuals? Second, what is the probability of observing between 85 and 95 HIV positive individuals? To do those calculations, we need to go ahead and open up Stata. So open Stata on your computer right now. So recall that the first thing we wanted to calculate is the probability that X is greater than 100. So we need to use either the binomial tail command or the binomial command. To use the binomial command, we would type display 1 minus binomial sample size equals to 500, 100, and prevalence is 0.178. Essentially what this does is we're calculating 1 minus the probability that X is less than or equal to 100. And this is going to be equal to the probability that X is greater than 100. On the other hand, we could have done the calculation in Stata using the binomial tail command by simply calculating the probability that X is greater than or equal to 101. So first, using the binomial command, we find that this probability is equal to about 9%. Now let's try out the binomial tail command. And we get the exact same answer. So this is showing you that you can use either 1 minus binomial or the binomial tail command to obtain this probability that X is greater than 100. But keep in mind, it's very, very important as to whether you're dealing with less than or equal to versus less than, greater than or equal to versus greater than, when you're dealing with discrete outcomes like in the binomial setting. So recall that the next thing we wanted to look at was the probability that X is between 85 and 95. Now we have to think pretty critically about how to do this in Stata using the binomial command or the binomial tail command. First, let's look at the binomial command. So the way that we could perform this calculation is we could calculate the probability that X is less than or equal to 95 and then subtract off the probability that X is less than or equal to 84. And this will give us exactly the probability that X is between 85 and 95. On the other hand, if we wanted to use the binomial tail command, what we would end up doing is we would need to calculate the probability that X is greater than or equal to 85, and then we would subtract off the probability that X is greater than or equal to 96. So now let's do those calculations in Stata. First, using the binomial command, we would do 500 as our sample size, 95 as our observed outcome, and prevalence 0.178, subtracting off. And again, subtracting off the probability that X is less than or equal to 84, we find that the probability is about 47.5%. Now let's use the binomial tail command. When we perform the calculation, the probability that x is greater than or equal to 85 minus the probability that x is greater than or equal to 86, we obtain the exact same probability. So you can use either binomial or binomial tail to achieve the same goals, but you need to think really hard about how you do it. So moving on, in the same example, instead of using the binomial distribution, let's say we decided to model the number of HIV positive individuals using the normal distribution instead. So same question, but as a statistician, we have the choice of what model to use. So now I'm going to choose to use the normal model. Now in this setting, what is going to be the expected value and the standard deviation of x? Well, essentially they're going to be the same thing. The expected value of x is equal to n times p, which we saw before is 89. The standard deviation of x, it's the same thing again. It's the square root of n times p times 1 minus p, which we saw was approximately equal to 8.55. So what ends up changing in this setting? Instead of saying x is binomially distributed, sample size 500, probability of HIV equal to 0.178, we're not using that model. Instead, we're saying we're modeling x using a normal distribution, mean 89, variance equal to 8.55 squared. So we've changed the model. And again, let's perform the exact same probability calculations that we did before. We want to know the probability that x is greater than 100. We also want to know the probability that x is between 85 and 95. But recall, we're using this normal model. So if we want to do these two probability calculations in Stata, the first thing we have to do is standardize. So we can't directly compute the probability that x is greater than 100. Instead, we're going to have to calculate the probability that z is greater than 100 minus the mean of 89 divided by the standard deviation of 8.55. So we calculate the probability, plugging that guy into a calculator, that z is greater than 1.286. And then this we can plug into Stata. All right, now let's look at this other problem over here. We want to know the probability that x is between 85 and 95. These should be strictly less than or equal to, but it doesn't really matter in this case since we're dealing with a continuous probability distribution now. In the binomial setting, it makes a big difference. Continuous setting, it doesn't make a difference. Okay, so to do this calculation, we would calculate the probability that x is less than or equal to 95 minus the probability that x is less than or equal to 85. But again, we have to standardize these two, so it would be the probability that z is less than or equal to 95 minus 89 divided by 8.55 minus the probability that z is less than 85 minus 89 divided by 8.55. Plugging those numbers into a calculator, we can calculate the probability z is less than or equal to 0.702 minus the probability that z is less than negative 0.468. This number we can get from Stata, and these two numbers we can get from Stata in order to do our probability calculations. So open up Stata on your computer now. So as a recap, we want to know the probability that z is greater than 1.286. We want to know the probability that z is less than 0.702, and we're going to subtract that from the probability that z is less than negative 0.468. So for the first calculation, we type display 1 minus normal 1.286, and we find that the probability of observing greater than 100 HIV positive individuals is about 9.9% when we use the normal distribution. To calculate the probability of observing between 85 and 95 HIV positive individuals, we're going to type display normal 0.702 minus normal negative 0.468. We find that this probability is about 43.9%. So the final question that we want to ask is, do the normal and binomial models give similar results? So for the probability that x is greater than 100, we found for the normal model it was about 9.9%. We found that for the binomial model, on the other hand, it was about 9.1%. So those results to me seem pretty similar. Looking at the probability of observing between 85 and 95 individuals, we found that for the binomial model, this probability was about 47.5%. On the other hand, for the normal model, we found that it was about 43.9%. So these are similar, but it seems like the approximation of the normal and binomial models is better in this example in the tails. So what do I mean by that? So you've got this distribution. It's centered at about 89, and we find that our calculation for observing whether x is greater than 100, that the binomial and normal models match up better out here in the tails than they do in here in the middle of the distribution. But in general, I think the approximation is good.